Thank you, Adam, for accepting our invitation. Adam Smith, a PhD student from the University of Sheffield. His title of the work is Axion-dilaton interactions in the dark sector. And Adam, you can start whenever you are ready.
Thank you very much. Thanks for inviting me also, Enrico. I'm very happy to be here, and I'm going to be talking about some of the work that I've been doing with these wonderful people at the bottom. Maria Mylova, Philip Brax, Cliff Burgess, and Anne Davis, and also my supervisor, Carsten Vanderbroek at Sheffield. And we're specifically interested in the late-time cosmological implications of the kinetic or two-derivative interactions between multiple scalar fields. And we specifically focus on a class of models called Axion-dilaton models. And I'll talk a little bit about what those are in a second. But I'm first essentially going to try and motivate why we think multiple scalar field models in the context of late-time cosmology are quite interesting, and specifically why kinetic interactions between them can also be interesting. And this comes from the observation that when you're doing late-time cosmology with these kinds of scalar field setups, you typically do it in the context of scalar tensor theory, which in the low-energy semi-classical limit of late-time cosmology behaves as some kind of derivative expansion. And what that means is that you can write an effective field theory Lagrangian for your theory, essentially in ascending powers of derivatives of interactions between scalar fields. And this is what it looks like here. It's a bit messy. But the observation is that as you go to higher and higher order interactions in terms of derivatives, you expect them to contribute less and less to your overall effective field theory. So if you're looking for things in terms of late-time cosmology that could give deviations from general relativity, which itself is a two-derivative interaction, you expect those to come from the three leading order terms that go up to two derivatives in your effective field theory. And I've written down what they are on this first line here. You have the zero derivative interactions, or the potential interactions between multiple scalar fields, which are labeled by V here. And theta is just some kind of label for these possible scalar fields. And when you're deriving this kind of stuff from fundamental theory, these kinds of interactions are typically quite dangerous. And you essentially need to provide some kind of reason as to why they're smaller than what's observed today with the cosmological constant. And you would typically do this with, for example, some kind of symmetry arguments like scaling symmetries and shift symmetries to try and suppress these kinds of interactions. And so unless you considered some effective field theory with some kind of symmetry breaking, the next best thing, and also the things that more naturally want to compete with general relativity in a non-dangerous way, are the two derivative interactions. And there are two of them, and I've written them down here. You have the direct interactions between scalar fields in the Einstein-Hilbert term, which is parameterized by this W function here. And typically, these kinds of interactions are very well constrained by local experiments, such as the Cassini probe in the solar system. And this means that essentially these things are very well constrained towards one at the present day, these types of W functions. And so unless you had some cosmological theory that differs from the local dynamics, or you had some kind of theory where this W function tends towards one at the present day, this would give rise to small deviations from general relativity and also the standard cosmological model as a result. And obviously there are many exceptions to this, but this is just a general statement that can be essentially applied to what we think is interesting at the moment. But you also have these other two derivative interactions, and you can see the two derivatives here on this third term. And these things essentially depend upon the gradients of scalar fields, and they're describing interactions between scalar fields through their kinetic terms, through this non-trivial field space metric Gij here. And these things aren't subject to the same kinds of local constraints as the direct couplings between essentially scalar fields and gravity, because they depend upon these gradients of scalar fields, which don't generically have to be there in the solar system, but they can very easily be there in cosmology, because these scalar fields could evolve with time. And so understanding what these kinds of things would give rise to in terms of late-time cosmology, we think is interesting. And so with these kinds of motivations, we zeroed in on what we think are the simplest possible examples of these kinetic interactions. And they essentially come from the Axion-dilaton class of models. And I've written down what these kinds of kinetic interactions look like here. And these models consist of a dilaton field, which is this chi scalar field here, and an axion-like particle, which is this A scalar field here. And you can see they're as simple as it possibly gets with these kinds of kinetic interactions, because the non-canonicalness only depends upon one of the terms, so this W function here. And it essentially depends upon the dilaton only, because it can't depend on the axion due to the axion's periodic shift symmetry. And so they're as simple as it possibly gets in terms of these kinetic interactions. And they're also extremely well motivated from the point of view of fundamental theory. And that's because these kinds of doublets of fields arise all the time in extra dimensional UV completions like string theory. What you typically find is that because these essentially UV complete theories are complex theories, you have to build complex scalars from essentially real and imaginary parts of real scalar fields. And these dilatons and axions pair up in this very characteristic way as the real and imaginary parts of these complex scalar fields. And this, essentially the dilaton in these kinds of fundamental theories is telling you, essentially parameterizing a volume modulus, or telling you the size of extra dimensions in these theories. And this exponential normalization of the real part of these complex scalar fields essentially just governs exactly what the kinetic coupling between the dilaton and the axion should be. You essentially find that this W function has to depend exponentially upon the dilaton through this kind of runaway exponential behavior. And this zeta parameter in the argument of the exponential is determining essentially the strength of the coupling between the dilaton and the axion. And so the point is that they're extremely well motivated from fundamental theory, and they're extremely well motivated also from the point of view of cosmological observables. And that's because these dilaton volume moduli arise in your effective field theory as scalars that are naturally light, just because of the form of their exponential scalar potentials. And so they can very naturally give rise to some kind of scalar that could be responsible for dark energy. And obviously these axion-like particles that they generically come coupled to have a wide range of uses in terms of late time phenomenology. And this is the most obvious case is, for example, when you give them some kind of quadratic potential, with a large mass, the scalar field will essentially oscillate very quickly in this quadratic potential, and so can describe some kind of cold dark matter species as a result. And so we have these two scalar fields that generically can couple together from fundamental theory that can also give rise to essentially the two main components of the dark sector in late time cosmology. And what we wanted to do was understand what these kinds of kinetic interactions between them might give rise to in terms of observational implications. And obviously, when you're doing this kind of stuff in late time cosmology, you have to consider the full action for your theory. And this is what it is for an Axion-dilaton theory. You essentially have the Einstein-Hilbert term, obviously, these Axion-dilaton kinetic terms, the Axion-dilaton scalar potentials, and also on the right-hand side, the Lagrangian for the rest of the standard model. And given that these kinds of dilaton fields arise from some kind of extra dimensional context, we know exactly how they should couple to the rest of the standard model. They will couple through this Jordan frame metric, which is G tilde here, related to the Einstein frame one by this exponential conformal transformation. And what this essentially boils down to when you can compute how masses of particles evolves is that the masses of all non-relativistic particles, and for example, baryons here, as I've written down, have this runaway exponential dependence on the dilaton field. And I say runaway because this G parameter here, this Brans-Dicke coupling constant, is essentially a negative constant always. And so this is essentially everything that you have to specify in terms of these dilaton fields for late time cosmology, how they couple to matter through these exponential couplings of the masses, how the dilaton couples to its paired axion, and also the scalar potentials for your axions and dilatons. And we choose to essentially complicate the story a little bit by essentially taking what's typically done with these kind of exponential dilaton potentials and modifying the prefactor U here with some kind of quadratic dependence on the dilaton field. And the reason we do this is to essentially tie in with what's been done so far in terms of early universe string phenomenology with these fields. So typically these dilaton volume moduli fields are used as some kind of inflaton fields or waterfall fields for inflationary setups. And then after the end of inflation, they would roll down these exponential potentials and then reach some kind of local minimum at late times. And these local minima are typically associated with reheating effects and essentially giving rise to essentially the standard hot Big Bang afterwards. And so what we wanted to do was essentially engineer some kind of local minimum in this exponential potential and use it as the initial conditions for the dilaton field at late times and just allowing it to evolve from the bottom of this local minimum by giving some kind of quadratic dependence of the prefactor here. And so this is what we did, and this is everything that you need to specify in terms of dilaton cosmology. The other thing is how we want to treat this axion-like particle that it comes coupled to. And we essentially do what's canonical in the literature. We expand around the minimum of these axion-like particles' periodic scalar potentials as some kind of quadratic. And then we write down some ansatz for how we want the axion-like particle to evolve. And we split it into two parts. the evolution of the vacuum expectation value, which is a bar here, and also the oscillations around this kind of quadratic minimum of the potential, which is described by this second term. And this psi field here is describing essentially the amplitude of the oscillations as the axion oscillates. And then you also have the rapid oscillations, which are essentially just modulating these psi fields, which are described by these rapidly oscillating phase factors. And what we use here is the effective mass of the axion field as some kind of measure for the frequency in the argument of the exponential, or the frequency of oscillations. And this is just because essentially if you have some kind of scalar field with an effective potential, the steeper the effective potential is, or the larger the mass is, the faster you expect it to oscillate. And so the effective mass plays the role of some kind of frequency of oscillations. And the effective mass in these kinds of theories is just the bare mass coming from from essentially just the vacuum scalar potential, weighted by the kinetic coupling between the dilaton and the axion through this W function on the right. And so we have this kind of ansatz for how we want these axion-like particles to evolve at late times. And if we substitute that back into the action, and we essentially go through all the horrible perturbation theory, and then essentially just focus on the background for now, we find that the energy density of these oscillations scales away like 1 over a cubed, exactly as you would expect for a non-relativistic particle species. But you now have the time evolution of the effective mass, which is going to give deviations from 1 over a cubed, because the effective mass now depends upon the dilaton field. And so this can give rise to observational deviations even at the background level for these cosmologies. And so just to sum that up, that's a lot of phenomenology of two different scalar fields before I essentially spend the last few minutes talking about the results. We essentially have these kinds of axion-like particles oscillating very quickly in these quadratic potentials, scaling away as 1 over a cubed, but with extra deviations coming from the kinetic coupling between the dilaton and the axion, which is now essentially baked into the effective mass of the axion field. And these kinds of kinetic couplings are always exponentials. And so it's very easy to see what they will do if you essentially look at the dilaton's Klein-Gordon equation. So as I said at the start, we essentially start the dilaton essentially just in this kind of local minimum, which was essentially responsible for reheating. And so this kind of local minimum will essentially stabilize the dilaton at late times and try to push it towards the minimum. But the coupling towards essentially everything else that's non-relativistic in your effective field theory will push the dilaton towards larger values because of this universal coupling. And so essentially, the dilaton will get pushed out of this kind of well. And in the single field stuff that has been derived so far, basically these cosmologies were deemed non-viable because you would have some WIMP-like species of dark matter. And this would couple in the same way baryons would, just by some non-relativistic coupling. And so essentially would just drive the dilaton down this exponential potential and stop it from acting as dark energy at late times. But what we're finding is that if you essentially prescribe the role of this kinetically coupled axion-like particle to to essentially the role of dark matter, it will essentially do the opposite thing because this zeta parameter in essentially the Klein-Gordon equation of the coupling between the dilaton and the axion is a positive constant. And so it will push the dilaton towards smaller values. And so what happens is that when the dark matter is dominant, it will be the dominant component in this Klein-Gordon equation and will push the dilaton back up the exponential potential instead of down it. And then at late times, the dilaton will just drop back down and oscillate in this kind of local minimum and describe dark energy as a result. So this is essentially holistically what's shown in these kinds of background plots of the cosmology. So here, what I'm plotting is essentially the energy density evolution of all of the different cosmological characters with time. So the dilaton is this orange line, and the dilaton's essentially potential energy is this brown line. And you can see that we've prescribed the role of this axion-like particle to cold dark matter, which is the blue line. And what we find is that the dilaton at early times enters into some kind of tracker solution and then settles down at late times to act as dark energy. But in these intermediate regimes where the axion-like particle is the dominant component, it will push the dilaton back up this kind of exponential scalar potential and give some kind of bump in energy density as a result. And this kind of bump in energy density will essentially kick the Hubble rate during matter domination, very late into matter domination. You can see it very easily in the fractional plots here. And so this will give rise to deviations in terms of three main things. And the first ones are just the deviations coming from the evolution of the dilaton field, which will cause correlated evolution in the evolution of the masses of all of the particles in your effective field theory. And so as the dilaton gets pushed back up his exponential scalar potential, the masses of all of these particles, which depend exponentially on the dilaton, will also evolve. And so that's straight away one thing that could be observed in terms of signatures of things like optical transitions with redshift space distortions and things like that. The other things are at the perturbative level. So this on the right here, I'm plotting essentially F sigma 8, which is just a product of sigma 8, which is the amplitude of matter perturbations in 8 megaparsec spheres, multiplied by F, which is just the normalized growth rate of matter perturbations with these essentially axion perturbations baked into them. And what we're finding is that this kind of, typically this kind of product of parameters is a cosmological observable. And so you can plot it against data points and see how it will change the fitting as a result. And what we're finding is that as you couple the dilaton more and more strongly to the axion and essentially draw it further and further up the exponential potential, it will give rise to larger and larger oscillations in structure growth as a result at late times. So this black line on the right here is just the lambda CDM line. And then we essentially just plot increased coupling strengths between the dilaton and the axion through the zeta parameter. And you can see it gives rise to larger and larger oscillations in structure growth, which could very easily fit the data very differently. And so that's a deviation in terms of structure growth. And the other thing that it gives deviations in terms of at the perturbative level is the angular and matter power spectra of the CMB. And so what I've plotted here is essentially the angular power spectrum on the left as a function of multipole and how it deviates from the lambda CDM line, which is the blue line. And what we find is that because these deviations are happening at very late times in the cosmology, just before the start of dark energy domination, the deviations that you see on the sky are essentially on large angular scales. And so they will give deviations in terms of the small multipoles of the angular power spectrum. And they essentially just look like late time integrated Sachs-Wolf effects. And you can see that these kinds of tails on the angular power spectrum get larger and larger as you increase the coupling strength between the dilaton and the axion. And so with this kind of stuff, you don't even need to do data analysis because, for example, this red line is already completely ruled out by CMB data, while these orange lines are within the realm of acceptability. And the other deviation in terms of power spectra is in terms of the matter power spectrum. And there's essentially a lot going on here in terms of deviations. And it's coming from things like deviations in Newtonian potentials, particle masses, and couplings between dark matter and dark energy. I'm not going to try to explain all of this stuff because it's kind of a mess in terms of deviations. But there are deviations there that could give rise to essentially different fittings to data as well. So just to essentially show the final thing before I show my conclusions, this is essentially, given the timely results of the DESI releases, what we wanted to do was also show how the effective equation of state of dark energy evolves in these kinds of models. And to compare with, for example, the DESI results, which assume that all other particle species are essentially decaying away as 1 over a cubed, at least the non-relativistic ones, you have to pull the couplings that are coming out from the couplings between this dilaton dark energy and the other particles and just give it to the dilaton field instead of the other components. So that essentially they scale away as 1 over a cubed while the dilaton gets these extra coupling energies. And so then you evaluate this kind of effective equation of state, which is just using the effective energy density of the dilaton, which is just essentially the dilaton energy plus these coupling energies. And on the left is essentially what this kind of effective equation of state looks like in late time cosmology. You find these kinds of bounces off the phantom divide line, followed by some eventual phantom crossing quite deep into matter radiation domination for redshifts of order 5, 6, 7, 8. And the redshift at which this transition happens is essentially increased as you increase the coupling strength between the dilaton and the axion. And given that these are very non-standard or non-linear, at least, evolutions in terms of the effective equation of state for dark energy, we think that it's essentially not apt to compare, for example, the linear approximations that are used by the DESI results with these kinds of things. So we would have to do some full data analysis to see if these kinds of things can be acceptable and also possibly preferred. So that's everything that I wanted to talk about. This is essentially my summary slide. So what we showed is that these axions and dilatons in these kinds of doublets can respectively play the role of dark matter and dark energy. And the interactions between essentially these two scalar fields in terms of their kinetic terms can give rise to oscillations in structure growth, oscillations in particle masses, and also deviations in terms of the angular and matter power spectra. Thanks for listening. I'm very happy to answer any questions.